Hello everybody, this is my talk on vocal markers of neuropsychiatric conditions, mapping the limits. I'm Riccardo Fusaroli from Aarhus University and an affiliated senior researcher at the Linguistic Data Consortium at the University of Pennsylvania. Before I even start, I should mention that I have potential conflict of interest in that the research that I'm going to show overlaps with some of my consultancies with Rush and the Children's Hospital of Philadelphia. So what am I going to talk about? Usually when introducing my work and my collaborators' work on vocal and speech markers of neuropsychiatric condition like autism, schizophrenia, and depression, I would rant for long on the importance of doing this. But fortunately in this group, I don't need to do that. And therefore, I'm going to do the opposite. I'm going to try to discuss the importance of understanding the limits of our conceptions of vocal markers and how our currently identified vocal markers in the literature, right? The things that we're doing wrong and some way forwards to do things better. So first, I will discuss where we are in the search for vocal markers, how much we have achieved, and which are the limits of these achievements. And I'll do this through a series of studies, first systematically reviewing and meta-analyzing statistical findings and machine learning findings on vocal markers of autism and schizophrenia, and then systematically stress testing these findings by replicating them on a novel cross-linguistic data set to see how well they could generalize. Finally, we'll try to push the study of vocal markers forward by trying to identify the lessons learned and by highlighting two cases in which we can integrate multiple sources of information to our analysis of clinical data. The first case, the use of spontaneous drug reports or spontaneous drug adverse events reports as studied by pharmacosurveillance to identify potentially drug-induced confounds. And the second is the use of transfer learning. That is the use of machine learning algorithms that have been pre-trained on other domains. But let's start with a personal tale. So I started investigating these topics about 10 years ago when at the coffee machine, as it often happens, I heard something interesting. Somebody was discussing how after working for many years on a specific cognitive ability within autism, the researcher was saying that they could hear certain atypicalities in the speech of their autistic participant. But whenever they look at the spectrogram and at the quantitative acoustic features of the voice, they could not find it. And there, I was just fresh of a humanistic PhD. I had just learned how to use MATLAB, and I was discovering this thing called machine learning. So I just jumped in the conversation, said, give me the data, hold my cup, and I'll produce a quantification of that. Took a bit longer than I thought, but I produced machine learning models that would separately work on data from depressed patients, schizophrenic patients, autistic patients. They would reach roughly an 80% out of sample accuracy. And I got really excited. Started presenting these results at a few conferences. I got handed novel data sets by people who equally got excited about being able to see in the voice complex neuropsychiatric conditions. And these novel data sets were where the problem started. As soon as I tried to use some of my old machine learning model trained on the old data sets on novel, otherwise similar data sets, nothing would generalize. These algorithms would perform a chance or almost. I could always take the algorithms, retrain them on the new data set, right, or train them on a combination of the two data sets, and the results would work again, right? About 80% accuracy, but with different features, different hyperparameter values, And while these taught me a lot about machine learning, it left me very dissatisfied and frustrated and disillusioned about whether, right, what I was doing had any value at all. Now, don't get me wrong, right? Having machine learning models that are very specific to a task, a language, a subpopulation in the clinical domain can be useful. We have really amazing algorithms that can trace motor degeneration in Parkinson if you bring the patients in the lab in front of a high quality microphone and have them do prolonged phonation. But at the same time, right, if we want to really bring more generally these vocal markers of neuropsychiatric conditions into the clinic, right, we need a more nuanced understanding of what generalizes. Right? For instance, even within participants, would these models predict the same thing over time if the voice was recorded in the clinic or at home, if it was recorded on a microphone or on an iPhone, if it was recorded while chatting with the clinicians or reading something aloud, right? What of these conditions, if it doesn't generalize, then would be best for investigating, you know, whatever clinical feature that might be relevant, right? So we've seen prolonged phonation could be useful for motor degeneration, but for emotional state, probably recounting one's day would be better. But in order to do clinical use, we need to figure out these things. We also need to figure out what generalizes between participants, right? If we get new potential patients, will the algorithm work out of the box or should we retrain the algorithm? What about diverse subpopulation, right? So if I train my model on a large urban population, let's say Copenhagen, and then I go in the deep rural Denmark, will that still apply even if the dialects, the socialites, and potentially even the clinical profile are different? But also, what about different population? Let's say that we have some fancy algorithm from the States. Can we apply it in Europe? What can be reused of that algorithm and what should we retrain? All of these are really crucial questions. Second, as I am a scientist, I'm also interested in what we gain in terms of understanding, right? By applying and investigating the generalizability of this machine learning algorithm of vocal markers, we can figure out what is specific to the condition and what isn't modulated instead by language and culture, right? Which might tell us something about mechanism. And on the contrary, if we have, on the other side, if we have some theoretical model of how the disorder works and the way it would apply to specific voice features, right? We can not only get potentially better machine learning algorithm, but we can also put these ideas to test, right? And learn something about whether these mechanisms really hold. So I started going back to basics, right? Scratched my conference posters, don't publish papers, and go back and read and investigate what has been done and how we could build a more principled approach to identifying vocal speech markers and their limits. And I'm going to say this is a total request, and you'll see that my trajectory still has huge holes in this respect. So we'll agree, this is work done with many of my collaborators. Key here are Ethan Weed for autism and Alberto Parola for schizophrenia. And we produced 2 systematic reviews and meta-analysis on vocal markers in autism and schizophrenia, covering in total more than 100 articles, more than 70 years of research, and more than 1,000 patients and equivalent controls for each of the 2 conditions. We will then compare what has been found there on 2 novel cross-linguistic data sets, which are used to stress test and replicate the findings from the meta-analysis. In the autistic novel data set, we have about 77 autistic Danish and US children doing repeated recordings for a total of more than 1,000 several recordings, retelling a story versus or describing a video to slightly different tasks. In the schizophrenia data set, we have about 231 patients with schizophrenia from Denmark, Germany, China, and Japan, again doing repeated measures while describing videos, and more than 4,000 recordings. Very quickly, if we just look at how these papers cite each other, even if they're all investigating very similar phenomena and quantifying very similar acoustic features, we can see on the right that green cluster, it's autism. It's relatively cohesive. Papers cite each other more than they cite papers in the purple or other clusters, which are the schizophrenia papers, but only 1 out of 3 of the possible sources of additional estimates and information, 1 out of 3 of the previously published papers is on average cited, and some papers are even isolated. That is, they don't cite any other paper from the field. If we look on the left, we see that schizophrenia is organized in 4 different clusters, 4 different groups that papers that cite each other more than they cite any other paper, and only 1 out of 4 of the previously published studies with concrete estimates and investigation is cited. So the field is very fragmented. When we look at the actual estimates that we can infer by combining all these studies, and we can identify a set of features that have been investigated and the average difference across studies between the patient and the control population, we see that in autism the pitch is higher and more varied with swings, right? When we look at measures of duration, the only reliable difference is pause number, with autistic individuals producing 0.4 standard deviation. All of these numbers are Z scores, so 0.4 standard deviations more pauses than the controls. When we look at different tasks that have been used to record these speech, there is no effect of whether it's a conversation or reading aloud, and the results are only mediumly robust to publication bias. That is, they disappear if we start assuming that publishing a significant finding is 5 times as likely as publishing a non-significant finding. If we look at schizophrenia, there's no really reliable effect on pitch. And when we look at duration, we see that pause length is the only reliable finding, but it has a humongous effect size of almost 0.2 standard deviations away with schizophrenics having longer pauses. Right? An effect size of that size could actually be a really promising marker of schizophrenia. Here, all these effects are bigger in the more free speech production than in the more constrained speech production like reading, but the robustness to publication bias, that is, if we were to assume that a significant finding is twice as likely to be published as a non-significant finding, we would get the estimates, and adjust for that, we would get that the estimates really start overlapping with 0. So the effects disappear and are likely fruit of publication bias. Well, let's put this to test, right? These are the results we've seen before. If we replicate for autism pitch results, we see that pitch mode is only higher in American children with autism, and the effect size is half that in the meta-analysis. And pitch variability is only higher in the Danish children with autism, and the effect size is about half. Pause length is found increased in both American and Danish children in the same direction as the meta-analysis, although the meta-analysis was not significant, was not statistically reliable. Nothing else is found. When we look at schizophrenia, pitch mode is higher only in Mandarin and Japanese, same size as in the meta-analysis, although the meta-analysis was not reliable. Pitch variability is lower across the board of the 4 languages investigated, but a smaller effect size. Speech rate is slower across the board, and nothing else replicate, not even the humongous, or especially not the humongous post-length effect. Take-home message, right? We can only find minimal cross-linguistically reliable vocal markers, and they are with small effect size. Out of 70 years of research, right, we haven't found a strong vocal markers that would replicate across the variation of having different languages on which to test it. And while one could say the cross-linguistic variability might be the culprit, I have to say that US English is the dominant um, language in the meta-analysis. And even when we have in our novel data sets American English in autism, the markers do not generally replicate. There is systematic heterogeneity, however, that we can observe both by language but also by clinical and demographic individual differences. There's more about this in the papers. I just don't have the time to see that. And there is other yet unsystematic heterogeneity, which could be further described if, for instance, we had access to medications and other things. That if we read the literature, mechanistic explanations are very rare and very phenomenologically based, and the results are not really giving us a hint as to where we should go. However, what we could hope is that this is because of the outdated methods, right? We're in 2022. Why should we take a single acoustic feature and one by one look at differences by group? We can do better. So we have the machine learning machine. We can use algorithms that are designed to be able to find nuanced combinations of values in the features that together can yield cues as to whether a diagnosis should be given or not. Right? And here is a paper where we discuss this. But when we look at the meta-analysis, indeed, we have that there are today 23 studies for autism, mostly using LDA and SVM, but more recently neural networks. The accuracy is between 70 and 96%. Schizophrenia has fewer studies, 9, and analogous accuracy range, 75 to 87.5. And there is no replication, however, within these studies. Even if they yield promise, none of them has taken the same model and tried it on a completely different data set. None of the studies take the methods from the previous study and more systematically and reuses them on a novel data set. If we look at the list of features to see whether there would be some features that recur more often, we see that between any two given studies, there is less than 10% average overlap. And there is no open code or data that could help us running replications of these studies. The situation is exactly the same for schizophrenia. Right. Well, we can take the way that these models are described, right, and start see whether these findings would replicate on our novel cross-linguistic dataset, right? And given the structure of our dataset, we can ask more nuanced questions. The very first one is, can we replicate the general performance of published algorithms within corpus? Right? Same language, same task, on held out balanced validation sets, right, of new participants speaking the same language and doing the same task. That's the traditional way of testing the performance of an algorithm. But we can stretch it further, right? We can say, how well does the Q1 trained algorithm, the algorithm from above, generalize to the same participants performing a related task? For instance, instead of retelling a story, they might be watching a video and having to describe it after, and vice versa. And even more radical, how well do these algorithms generalize to participants with a similar demographic and clinical profile, but speaking a different language? So this is actually quite amazing work made by Emil, Maria, Stine, Astrid, and Alberto, where they developed a pipeline, pretty conservative pipeline, where the data gets pre-processed, partitioned, normalized. There's a feature reduction paradigm, there's model training, parameter tuning, model testing, and once we're satisfied with that, there is a completely separated holdout validation set that we use to calculate the actual performance. And the pipeline is very modular, so we can just plug and play different ways of doing data partitioning, different ways of extracting features, different ways of normalizing feature, different algorithms, right? And so on and so forth. And here I'm just going to show the results from the replication using SVM models from those two papers, Markey et al. 2015 and Chakraborty et al. 2018. What we see is on the first column, the meta-analysis accuracy scores. I have to warn you, they are relatively uncertain because I tried to reconstruct F1 from accuracy when they had sensitivity and specificity, but I'm not really sure that things are the way they should be. But we can see that they're in the range that we were discussing before. Red for autism, blue for schizophrenia. When we do replication, second column within corpus, question 1, we have that we can achieve similar levels of performance as the published results. Right? We're slightly lower, but we're being more conservative than most of the studies, so I can live with that. I should also mention, why are there these many data points? Well, it's because, as for instance, we train models in different languages, like separately on each language, we have multiple within corpus performance. So that gives you a better idea of the distribution of accuracies that we can achieve. When we look at between tasks, for which we only have the autistic data, we see that the performance tendentially decreases. And when we look at the between languages performance, the performance reaches chance level. Meaning that the models can generalize to novel participants less well to different tasks and not at all across languages. Said that, so why is this, right? So first we argue that this is plausibly the case for all the published models that we tried, even if we don't have access to the actual trained models. And we argue that in domains with large heterogeneity, demographic, clinical, cognitive, etc., like vocal markers for neuropsychiatric domains, we cannot rely on limited sample sizes, which have been used throughout the literature. We really need diverse participants with metadata, diverse contexts, and many repeated measures to capture the heterogeneity of the phenomenon that we're trying to capture. We need collaborative and cumulative efforts, right? We need to share pipelines, code, and models, even when we cannot share the data, because that allows us to check upon each other and build on each other's work and replicate and see where things generalize and not. There might be models that generalize better than others. We just don't know because nobody's doing that. But while we wait and work to make this change happen, are there things that we can do? And I'm going to show you two examples of things that we have attempted, where we try to integrate information from additional sources so that our machine learning algorithm doesn't just rely on the limited clinical sample size and get stuck into the local minima. Right? The first one is work that was done with my brother, Michele Fusaroli, on potential drug-induced confounds. When we collect data, right, participants often report a wide variety of medication, doses, and administration methods. However, our limited sample sizes, right, are too small to do much beyond very rough analysis of drug classes. For instance, antipsychotics converted to clozapine scale. And that really reductive compare the wide range of medications that we see, right? And that we know might affect in many different ways vocal patterns, and therefore might make the algorithm overfit to that specific combination distribution of medications that we see in our limited sample size. Well, there is a whole discipline in which my brother is an expert called pharmacovigilance that attempts to track drug-induced adverse events integrating pre-marketing clinical trial information, what's usually in the side effects in the little piece of paper in the drugs, and using spontaneous reports generated by clinicians and patients about unexpected potential side effects. Right? Can we use these to identify potential cautions? Well, we collected a relatively large team with diverse competencies, speech and language pathologists, psychologists, medical doctors, cognitive scientists, linguists, and took the different ways in which side effects can be expressed in these spontaneous reports. There's a coding system, and identified specific groups of terms that could be used to define side effects related to speech and voice atypicalities. They're represented here: aphasia, phonatory problems, motor control or execution problems, prosody problems, incoherence, etc. We then fed it to the several million reports that are present in the FDA global dataset to identify which of these side effects were disproportionately present with which drug, or in other words, which drug were associated with the disproportional presence of these side effects. Given that an observed association between a drug and an adverse event could be due to many different causal mechanisms, we set up a basic causal inference pipeline that would identify these potential confounds using medical knowledge and set up control analysis that would try to rule out the presence of a confound. The drug adverse event associations that survived these theory-driven causal inference analysis were then aggregated with the already known side effects related to speech and voice from the clinical trials before marketing of the drugs and created a list, which can be seen here. Right? These initial list of drugs can be used to first try to identify which different mechanisms could be involved in different kinds of communication atypicalities, because we know the active principles in these drugs and what is common and not common to different drugs that are causing the same side effect. But also to provide a tentative list of drugs to be cautious about for all the new data collection. And if you go and look at the preprint, which is down there, the list is long, but of course we wouldn't expect that all of these drugs would be differently present in specific populations. We can just use it as an initial source of potential cautions we should take into account. The second approach is transfer learning. Here is done with Lasse Hansen and Kostas Sakidis, where we build models, for instance, that might be based on theory-driven hypotheses. There's phenomenological reports of sadness in Parkinson's and depression, right? That is, the voice of these patients tend to sound sad, even beyond their reported emotional state. And so what we did was to train speech emotion recognition to identify sadness and happiness in voice. And given the open data that were available, we trained this on German and English data. We then used these trained algorithms to assess the presence or not of Parkinson in Parkinsonian patients and controls voices from Spain, and people with depression, controls, and remitted patients in Denmark. And we could see that these models off the shelf without any retraining on the new data were actually able to find patterns above chance, which is promising for the results. It's nothing that we could use in a clinic, but it's a proof of concept. More generally, and this is work with Lasse Hansen and Roberta Rocca, we have that there have been attempts to create foundational models of language, deep neural network techniques, which have been used to automatically learn the most appropriate features for a problem, for instance, speech recognition and semantic representation on large A-specific data sets. And what we were wondering is whether we could use them as is or fine-tuned on our limited clinical sample size, right? The features are not the ones that we used before coming from speech signal processing, but those that have been automatically identified by these models. And here we compare adult populations from Denmark, some with an autism diagnosis, some with a depression diagnosis, some with a schizophrenia diagnosis, and mesh control for each of the groups. You can see here in red the baseline models that we were using, for instance, in the previous studies that I discussed, and in blue the transformer models, the pre-trained models. Right? We can see across the board on the plot on the left that when facing a traditional problem, can we discriminate between autism and mesh control, depression and mesh control, schizophrenia and mesh control? Right? The transformer are giving a relatively similar performance. They're not a magic wand, but there are some cases in which there is promise of better performance. However, when we open up Pandora's box and say, well, in the clinical world panel on the right, you don't often have a clear choice between schizophrenic or non-schizophrenic, but you have a patient that has some distress and multiple possible diagnoses with partially overlapping or similar clinical features. So if we then give the problem of separating from autism and everything else, depression and everything else, schizophrenia and everything else, what we see is that the performance actually decreases compared to the binary choice. Meaning that we have a specificity problem. The vocal markers that we identify, both with the baseline models and with the transformer models, tend not to be 100% specific to a given diagnosis, even in this limited set that we have. Here we have some confusion metrics, but I'm going to skip over that. Just want to go to the take-home message that just using these fancy off-the-shelf transformers is not going to work. Right? Transfer learning is promising. It's not going to be a magic wand, and that the specificity of the vocal markers is an issue. Still, I think we could do better by making more theory-driven transformer development, training tests that are not the predict the next word, as many of those data sets have been trained for and algorithms have been trained for, but more specific training tasks, let's say identify whether the same person or not has produced this text, and so on and so forth. These kind of different tasks, if well studied, might better translate to our problem. Also, we need more data on which, instead of using the algorithms as are, we might fine-tune them and still have an external validation set. So what should we do now? As I mentioned, we need larger open cross-linguistic data sets, clinical and not, because we've seen that maybe transfer learning can help. We need easier to share pipelines and motivated algorithms to reciprocally check on each other's work and build upon that. We need more theory and generative models, and I'm very aware that I've fallen short so far on doing that, but I'm going to keep on repeating them, if nothing else, to just put myself on the spot, and one largely unexplored side in my work, but I know you already have started investigating this, that is a more in-depth consideration of ethical concerns and participatory design involving both clinicians but also patients and their families, right? We all work, at least to start with the low-hanging fruit of clearly diagnosed versus clearly known psychiatric controls. Is this really a relevant problem, or is it only a convenient problem? It's harder than we thought, as I tried to demonstrate. But when I talk to patients, it doesn't seem to be something that it's really one of their concerns, at least not when they come to my lab, right, with already a diagnosis. Wouldn't, for instance, wouldn't there be better targets, clinically and personally relevant features of the conditions in which they are, where we could, be better able to assess them than, with supporting clinicians on to reach better intercodal reliability, for instance, and more objective assessments. But perhaps more crucially for the patients, right? Could we use these to identify individual variations over time, which could be used to give feedback to both the clinician and the patient, right? And give them a sense of agency on, or more control on what's happening to them, and hopefully some operational insight. And with that, I thank you, and I thank the long list of collaborators on these projects.